using mathematical reasoning, you can be an informed citizen and understand what's going on and not blindly trust any one of these. Meanwhile, Snowden is kind of stuck now because he managed to escape from the US, from the NSA, and found safety in Russia. But apparently Russia's not going to let him stay much longer. At least if you see the Q post, they said, haha, like, you were banking on the CIA director to save you. You were banking on, Hillary Clinton to invite you back, but you didn't realize that we would change the CIA director and the president would also change. And, do you have anything left to sell to Russia to preserve your safety there? Because once you run out, then they're not going to keep you safe there anymore. Well, I think if you just take a step back from all the things in the world, and all the laundry that you have to do, and do some math. If I were Snowden, I would just relinquish ties with Russia and the US. Don't work for either of them. And go teach programming at the University of Calcutta or something. Because, man, these universities, they would be clamoring, they are clamoring for people with proven skills like Snowden. And it's not hard to find a university that's not in Russia or the US. Thanks. Now let's get on to the math. So, as you can see, it takes some mathematical reasoning to make the right decisions and understand what's actually going on in the world and be an informed citizen. And then it also takes some multi-dimensional thinking beyond the box, beyond the Russia and US, beyond your country, beyond your field, major field. So beyond government, politics, and into, say, academics or something else. And maybe even beyond math into, say, spirituality. But that's a different story. Well, math is a very good way to exercise this thinking outside of the box. My favorite thing to teach is calculus. And why do I choose to teach calculus today? Well, partly because it's my favorite thing to teach, and partly because, well, there are a lot of free math content on the internet nowadays, but not a lot of free math content at college level. And I think it's really unfair for students to have to suffer the experience of college, plus how expensive it is, just so that they can get a glimpse of these mathematical contents beyond calculus, or at least beyond calculus 1. So here I've got all three in one book. I don't know if you can see that clearly, but this is the book that I like to use. And it's got calculus 1, 2, and 3. Anyways, there's calculus 1. And here's some getting into some calculus 2. And here's calculus 3. All in one small book. And it's very good quality. Good quality content. It's called Essential Calculus. By James Stewart. Yeah. Mine is second edition. I'm sure that that's already old now. So I'm not gonna, I think that they can all be taught together. Makes more sense to me. Calculus 1, because what's the difference between calculus 1 through 3? Calculus 1 is basically one-dimensional. So it's about functions of one variable. Calculus 2, you'll start seeing things like this, a function of two variables. But also, it's more like in between 1D and 2D. And also, I'm not sure if you can call it 1D, because it's actually in 2D space. We'll see what that looks like soon. Calculus 3, sometimes you're going to see functions of three variables. But it's really the in-between, because this is in 3D space. So I don't know if you call this a 3D function or 2D function, because it's got two variables, but it's plotted in 3 dimensions. This one is a function of 3 variables, but it's plotted in 4 dimensions. Alright, so what does this look like? Here's x. X is a number line. It can range from 0 to 1, -1, and it just keeps going. And here's the, oops. We usually draw it this way. The y-axis. I'm just going to be lazy and not include the arrows in the future. But just know that this goes on and on forever. So f of x, y equals f of x, that's going to look like some function, some shape. We'll label it that way, and obviously it just keeps going on and on. But it might not. It could be any shape. And then here, if you want to visualize what a function of 2 variables looks like, well, you'll have to do 2 variables which determine the function value. So given any xy pair, you're going to get a different function value. And if you do that for every single xy pair, put it together, you're going to get a surface that looks like this, some sort of shape. Alright, calculus 3. What does a function of 3 variables look like? Well, first of all, the 3 variables that the function depends on would be every triplet in this 3D space. And for each one of these points, there's going to be some function definition, function value. I can't draw, unfortunately, 4D coordinate axes on this 2D table. So each one of these is going to have some function value associated with it. Or maybe none. Maybe this one, maybe W is not defined at this XYZ triplet. Right? You could be like, oh, you know, the function looks like this. It's just not defined between like 0 or between like 1/3 and 1 or something. It could look like that. So calculus, what we do is we take these functions and essentially do 2 things. It's all about derivatives and integrals. If I were to sum up calculus, that's how I sum it up. You can take the derivative of a function, you can take the integral of a function. It was discovered by Newton, who was using derivatives. Actually, I think he came up with derivatives, but who knows? I mean, Newton himself says that we stand on the shoulder of giants, so he knows that it's possible someone unknown to him discovered it before, unknown to us. So he was using derivatives to study, obviously, gravity and how the planets move and how gravity affects that. And he came up with calculus. This was the birth of calculus, as we know it at least. And then both Newton and Leibniz independently came up with integrals. So yeah, the notation for an integral is called Leibniz notation, and there's a Newton-Leibniz theorem, I think. I don't know. I don't care that much about names. I'll talk about all these theorems anyways. We know what they mean. Alright, so let's at least figure out what derivatives and integrals are. And the rest of calculus basically is variations of these. Of course, in calculus 2, we also care about series. Sequences and series. pretty easy to take the derivative of a 1D function. It's called f prime of x. It's also called df dx. And there are a few definitions. The official math definition of a derivative of a function of one variable, at least, is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And there are other ways of defining the derivative as well. It's also, graphically what it means is if you take the point x, then f prime of x is the slope of the tangent line here. And another way to find the derivative, you could also get it in terms of known derivatives. So we also know that the derivative of f plus g equals the derivative of f plus the derivative of g. That's the addition rule. We know the product rule, so the derivative of f times g equals the derivative of f times the derivative of g plus the plus f times the derivative of g. And then we know the chain rule, which is the derivative of f of g is the derivative of f with respect to g times the derivative of g. By the way, when I say g prime, I really mean g prime of x. So whenever I say f or just g, I really mean f of x, g of x. Because in 1D, all our functions are functions of one variable, and there's only one variable, and it's called x. Yeah. And all the things that we know about derivatives, they come from these. In fact, you can get this and this all from the official math definition. Alright, so now let's look at 2D, and I'm running out of space. I'm just going to clear this out. Well, are you going to take the derivative, that limit there, with respect to x or with respect to y? I mean, it's hard to write that limit with respect to both. So in 2D, we define something called the partial derivative, which is, we can call it like the partial derivative of f with respect to y, with respect to x. And normally I'm going to be lazy and not include this parentheses x, y, but the first time I will. And so this is one way of writing the partial derivative, this is another way. And the partial derivative is defined as the limit as h goes to 0 of f of x plus h, y, minus f of x, y, all divided by h. So it's defined at every x, y. There is a different partial derivative at every point on this function. And it actually does correspond to the slope in a sense. We're in two variables. For simplicity, let's call this x. Call this y. So let's say at this particular x comma y, so in the xy plane, it corresponds to this particular function value point on the function. This is the function. Alright, and then at this point, when we take the partial derivative with respect to x, what does it correspond to in this diagram? Well, it's very similar to the previous diagram, which is it's the slope, the change in f divided by the change per change in x. So the up and down change versus the right and left change. So that means that if you draw the slope of this along x, so here is just tracing f going straight right and left, and f or z goes up and down. And then that creates a function similar to that one. And you draw the slope of that function at this point. Or you draw the tangent line. Then the slope of this is the partial derivative with respect to x. Similarly, you could take the partial derivative with respect to y. Then you just put the h here, and the slope would be the slope along the y direction. So partial f, partial y, or also that. It's gonna be the same thing except using y instead of x. This here is the ditto mark. It means same thing as before, but I put this y here to mean it's gonna be related to y. Alright, and now we have partial derivatives, but can we make a can we come up with an idea of a derivative of both at the same time? And yes, we can. It's called the gradient. Looks like that. And it is defined as a vector, which is very similar to a point. So it just has multiple elements in it. And in this case, the first element is partial f, partial x. y. The only difference between a vector and a point is a point looks like that. And a vector looks like that. So a point is just the location, x comma y. But the vector is an arrow that points to that location, x comma y. One is written with parentheses, one is written with angle brackets. So looks like we're going to have to learn some things about vectors if we're going to continue on with this derivative. So that's why calculus is not just about integrals and derivatives, it's not just about sequences and series. Starting at calculus 2 and above, I should write that this is 3D technically. We're going to also learn about vectors. They're so useful. It's not just about learning about planetary motion and gravity and physics, classical mechanics. It's so useful just for understanding how our world works. Rates, accelerations, distances, yeah, just motion in general. And then with vectors, you can do some things really easily that would be so hard to do using just geometry. For example, the law of cosines. How can you prove that for any triangle, c squared equals a squared plus b squared minus 2ab cosine theta? It is really hard to prove using straight geometry, but it's super easy using vectors. At this point, you might also be wondering, why do we stop at functions of 1 variable, 2 variables, 3 variables? I mean, we could also go on to functions of any number of variables, that you could just be like, the last thing is the function of the first n things. Yeah, we could do functions of any number of variables, but then you'd be working with, n dimensions. Quotation marks. And there's not that many n-dimensional things in our everyday physical life. Obviously, there are n-dimensional things in, like, data, networks with, like, n characteristics, abstract. So this is useful for a lot of abstract worlds. It'd be like, okay, we've got a Facebook network, and there are so many different people in the world, maybe 1 billion, and then each one of them has a function value. Okay, let's not care about the connections between these dots, but each one of them has some function value. This would be n equals a billion people on Facebook, hypothetically. And this is x n plus 1, or in other words, the function value. So you could be like, okay, for each of these people, dagnabbit, I meant, whether this person is like a level 1 user, or a level 2, or a level 3, or level 4, or level 3.5 user. Depends on certain variables, like they might have a certain number of followers, have a certain number of friends, have a certain number of posts, alright, and then some function of these determines what type of user they are. So this is n variables. And I mean, it's not just followers, friends, posts, there's other things about Facebook, people on Facebook. But the reason why do we only teach calculus 1 through 3? Well, because, I mean, not, like, most people in the world, or at least in the US, they're going to see some glimpse of calculus, because they have to care about one-dimensional functions, and whether you go forward or back. Yeah. You go forward, you could go backward. And then, I find this really, it has ties to, also how modernized we are, and how evolved our thinking is. In the ancient days, when there weren't that many people, like maybe in 300 BC, you only really needed to care about what's right in front of you. Are you increasing in food or decreasing in food? Survival. And then later on, as so maybe the world's population was like some 100,000 at most. And then maybe later on there was like some million. And then you started having to care about more than just, is it giving me food or is it not giving me food? Then you have to care about multiple variables, like I could go north, south, east, or west. This might have been around like the Renaissance, somewhere around 1700, or I forgot. And nowadays we care about a lot of variables. It's not just about where you are, it's also about what you think. So like, you could be in the US, but then you could be like Republican, Democrat. all sorts of things. And now we've got 6.0, more like 7 billion people on the planet. And you need to care about all these factors in order to survive. You can't just survive by going wherever there's food and taking whatever food there is. But also we care about 3D because that's about as far, like, most of our world is 3D. In fact, our world is basically 3 dimensions of space and then another dimension of time. At least that's the traditional way of seeing things. There are people who are arguing that there's actually 3 dimensions of time. And, well, I mean, it just depends on how you look at things. You might even go beyond 3D, ND, or there might be infinite dimensions, and then there might be dimensions beyond all of these dimensions. If you think outside of the board and go this direction instead of this direction. But that's not what we're going to, that's not what we usually teach in this setting, at least. So, just missing one more topic, which is how to take a derivative and integral in 3 space. Well, in 3 space, in 4 space, okay. Obviously, we still have partial derivatives. And then we still have the gradient. Except now, the gradient has multiple, more elements. And maybe eventually there's going to be like a gradient, which is something that involves the gradient. Gradient 1, gradient 2. And then we might just skip linearity altogether and, okay. This is just a little thing for you to wonder about. As it turns out, when you, there is something beyond all of this. It's called a quaternion. It was discovered by, I believe, Lorenz. A different Lorenz. And might have been discovered by, there was another person involved in the study of quaternions as well. But in here there's nothing new, it's just derivatives, gradient. We can, however, do cross products. And that leads to the curl. And there's also something called the divergence. We'll get to those with vector calculus. Thanks for watching. That's all for today.